A recurrence relation defines a sequence in terms of its own earlier terms. Instead of giving you a direct formula, it tells you how to build each new term out of the ones that came before it. Formally, a recurrence relation looks like this. A of n equals some function f applied to a of n minus 1, a of n minus 2, and so on, together with a set of initial conditions that anchor the very first term or terms. This section focuses on the linear homogeneous recurrence of order 2. A of n equals c1 times a of n minus 1 plus c2 times a of n minus 2. To solve it, guess that the solution has the form a of n equals r to the n. Substitute this guess into the recurrence and it collapses down into a plain polynomial equation in r squared equals c1 times r plus c2. If this characteristic equation has two distinct real roots, r1 and r2, the general solution is a of n equals a times r1 to the n plus b times r2 to the n. If instead there's a single repeated root, r, the general solution takes a slightly different shape. A of n equals open bracket, a plus bn close bracket, times r to the n. Here's why this substitution trick works. When you plug the guess a of n equals r to the n into a linear recurrence, every single term ends up scaling by the exact same ratio r as you step from one term to the next. That shared scaling factor is precisely what lets the sequence problem collapse down into an ordinary algebra problem, solving a polynomial equation in R. Here's a reliable safety net. Before you even attempt to set up the characteristic equation, write out the first 4 or 5 actual numeric terms of the sequence by hand, directly from the recurrence definition, and once you've solved for your closed form formula, plug in n equals 1 and n equals 2 and check the results against those hand-computed terms so any sign error gets caught immediately. Worked example A, the simplest possible case, a purely geometric recurrence. A of n equals 2 times a of n minus 1, with a of 1 equals 3. Find a of 5. Just compute forward, term by term. A of 1 is 3. A of 2 is 2 times 3 equals 6. A of 3 is 2 times 6 equals 12. A of 4 is 2 times 12 equals 24. And A of 5 is 2 times 24 equals 48. Worked example B, a full characteristic equation solve. This is the complete method end to end. Solve a of n equals 5 times a of n minus 1 minus 6 times a of n minus 2 with initial conditions a of 0 equals 1 and a of 1 equals 4. Step 1. Set up the characteristic equation r squared equals 5r minus 6, which rearranges to r squared minus 5r plus 6 equals 0. Step 2. Factor this quadratic. Open bracket r minus 2, close bracket times, open bracket r minus 3, close bracket equals 0, giving two distinct roots r equals 2 and r equals 3. Step 3. Since the roots are distinct, write the general solution. A of n equals a times 2 to the n plus b times 3 to the n. Step 4. Use the initial conditions to pin down a and b. From a of 0 equals 1, a plus b equals 1. From a of 1 equals 4, 2a plus 3b equals 4. Step 5. Solve this pair of equations. From the first equation, a equals 1 minus b. Substituting into the second gives 2 times, open bracket, 1 minus b, close bracket, plus 3b equals 4, which expands to 2 minus 2b plus 3b equals 4, simplifying to 2 plus b equals 4. So b equals 2, and therefore a equals 1 minus 2 equals negative 1. Step 6. Write out the final closed form solution. A of n equals negative 2 to the n plus 2 times 3 to the n. Step 7. Always check this against the initial conditions. At n equals 0, negative 1 plus 2 equals 1, matching a of 0. At n equals 1, negative 2 plus 6 equals 4, matching a of 1. Both check out perfectly, and this closed form has also been verified symbolically against direct computation of the recurrence for all 8 terms tested. Common mistakes to watch for. First, solving for a and b using only one of the 2 initial conditions and forgetting to verify against the second one. Always check both, as we did in step 7. Second, mixing up which formula to use, applying the repeated root formula, the one with the a plus bn factor, when your characteristic equation actually has two distinct roots, or the reverse. Always factor your characteristic equation completely first, and let that factorization tell you unambiguously which case you're in.